Today I will talk about some earlier work on estimating model errors, specifically due to unresolved subgrid scale processes in systems resembling the multi-scale Lorenz 96. And I'd just like to acknowledge my co-author, Peter Jan van Leuven, and also thank you to Sebastian Reich and Georg Gottwald. So the main motivation for this work is in improving ensemble data assimilation outcomes. And as I mentioned, I'm mainly interested in looking at model uncertainty due to unresolved subgrid scale processes, but it's of course important to characterize both observation and model uncertainty accurately in order to ensure that your posterior distributions are as optimal as possible. So the main purpose of this work, the main purpose of this talk is really to demonstrate the potential of some ideas for tackling model error in a fairly idealized setting, and also to demonstrate the potential of some fairly common assumptions, the pitfalls of some fairly common assumptions and approaches. So the problem setting that we're considering in this scenario is as follows. We have a system with states x with time index j. Evolution is guided by this stochastic difference equation with some deterministic model M, and the uncertainty in transitioning from time j minus 1 to j is captured by this additive model error term. And I've deliberately not specified any parametric assumptions or structure on this eta because I want to keep it as general as possible. We also assume that we have observations of the system available in this form where the observation operator is linear and the observation errors are unbiased and Gaussian. So of course, the goal of filtering is to estimate this posterior density or conditional density of the states given the data up until the current time, taking into account the uncertainties in both the states and the observations. So the system of interest here is the multi-scale Lorenz 96 system that you're all probably familiar with. So we have some coarse scale or resolved variables on this inner ring here, each of which are coupled to some high-frequency oscillating fast scale variables, which are on this outer ring. So there's actually a sizable body of research that you're also probably fairly familiar with that looks at how to parameterize the effects of these fine-scale processes on the coarse scale variables, both from a stochastic point of view and a deterministic point of view. For example, Wilks and Cromlin and Van den Einden. What we're proposing here today is to some extent inspired by these approaches, but tries to build on it in that we're trying to estimate the distribution of these etas for these following very specific conditions. So we assume that we don't have any dynamical equations of the fine-scale process, and also only partial observations of the resolved or the coarse scale process. So unfortunately, these parameterization schemes don't work for this setting because they all require data of the fine-scale process. So in equations, the system that we're dealing with is of this form. So the coarse scale variables are the x's, the fine scale variables are the y's. And the assumption is that we only have access to this equation in blue. And the effects of the fine scale processes are captured by this subgrid tendency term. And this is effectively the eta term that we're trying to estimate using only partial observations of this x. Okay, so we need to impose some regularizing assumptions in order to solve this problem, but we want to keep them as minimal as possible. So we assume that the states are directly but partially observed. So H is a 0-1 matrix. We also assume that the model error depends on some informative variable. So for instance, the state at the previous time or some reduced form of it. We also assume for now that the magnitude of the observation error is negligible in comparison to the magnitude of the model error. And we also assume that the etas arise from a stationary process and that the conditional density of these etas given the informative covariate is the same in both time and space. So this is this translation invariance property. So the proposed method can basically be broken down into 3 steps. Initially, we start off with generating a sample of these eta values offline using model simulations and partial observations. Once we've generated these etas, we then do conditional density estimation given this informative covariate using, for instance, kernel methods. So we want to keep things non-parametric. And finally, all that remains is to then sample from this density during an assimilation process, specifically an ensemble assimilation process. So you would propagate your ensemble through your forward model and then sample from this density and add these samples to each of your ensembles or particles. So I'll just discuss that first step of the method, giving just a broad overview of it. It relies on some fairly simple concepts. So if we have a time series of length capital T, the aim is to estimate, to optimize, the errors on the unobserved variables over a time window of length u. So that's shorter than the t. And we want to optimize these errors conditioned on this equality constraint, that the observations match the predictions of the observed variables exactly. So if we make this constraint and we also fix an initial condition and provide an initial guess for the errors on the unobserved variables over the time window, we can then do this sequence of operations to generate a sample of eta values. So once this is optimized, we then move over by one sub-interval and then repeat the process and continue until the whole time series is covered. So this, the motivation for this kind of sliding window approach comes from long window weak constraint 40 var. And the idea there is that you can essentially approximately neglect the background error term. So this is this error term in the this term in the cost function that relates to the initial condition error. And the rationale behind that is that because you have these overlapping windows, repeated iterations of this optimization process will then mean that the background term has converged. So it's effectively a constant that you can ignore. Okay, so how do we actually optimize these errors to generate a sample of etas? So the idea is to minimize the total conditional variance. So this is in some sense similar to least squares, but we formulate it in this way because we're rather interested in the distribution of the errors rather than the conditional mean function. And we also may run into heteroscedasticity, and we want to avoid any sort of parametric assumptions. So practically speaking, we estimate this via a simple numerical integration trapezoidal rule, because in this scenario, we're dealing with essentially 1D response variables. So we partition the covariate space, which can be higher than 1D, and then essentially calculate the sample variance in each of these bins of the etas. So here we really focus on the variance rather than the full covariance matrix, because we're assuming that these etas, the elements of the eta vector are conditionally independent given the state. So in order to test the effectiveness of the proposed approach, we had to look at a few benchmarks. And as I mentioned, the existing parameterization schemes aren't really amenable to our particular problem setting because we don't have access to the fine scale processes. So I've just looked at two relatively common but fairly simple approaches for characterizing model error in data assimilation. So the first is an analysis increment-based method, which basically assumes that the model errors can be characterized by a Gaussian, where the mean and covariance is estimated from sample statistics of analysis increments. So that's this delta xj term here. And analysis increments is essentially just the difference between an analysis and a prior at a particular time during an assimilation run. The second approach is kind of a hybrid of what we're proposing and long window weak constraint 40 var of Tremolay that I mentioned earlier. So the only thing that we're varying here is the cost function in the optimization approach. So we're still doing all of the density estimation. And here the reasoning behind this is really just to test the benefit of this conditional variance minimization approach. So here we have just a fixed covariance matrix Q that has to be specified. And also, as I mentioned, we no longer have this background error term. Okay, so we performed some numerical experiments with the multi-scale Lorenz 96 with two different chaotic regimes. The first involves a large timescale separation, and this was originally considered by Fatkulin and Van den Einden. And it has a nice error structure, so it's a good sort of test case for us to look at. But this large timescale separation is not so realistic, so we looked at a smaller timescale separation in this second case study, which is a bit more realistic and also slightly more difficult to parameterize. So as I mentioned earlier, we have observation sparsity both in time and in space, so only every second coarse scale variable is measured. And also we invoke this negligible observation error assumption. So these observation error variances are small in comparison to the model error conditional variances. Okay, so first just looking at the resulting eta samples from this offline error estimation. In this first case study, we've chosen the state at the same grid point as the informative covariate. This is quite commonly taken for this particular regime. And on the left, we have the true error structure. And on the last three show the different error estimation schemes. And obviously, you can see the proposed method reflects the true error structure much more closely than any of the more simple benchmarks. In particular, the analysis increment method performs relatively poorly because it also includes errors associated with the actual assimilation process. So for instance, the suboptimality due to inflation, etc. The second case study gives a fairly similar story. I've just put this here to demonstrate the use of a high-dimensional, not high-dimensional, but higher-dimensional covariate space. So here, not only are the errors dependent on the state at the current grid point, but also at the neighboring grid point. And the colors represent the magnitude of the errors. And as I mentioned, yeah, it's a similar sort of story. The differences are a little bit more subtle. You get improvements in certain regions using the proposed method compared to this using the 40 var as your optimizing objective function. Okay, so what's the benefit of actually doing this conditional variance over just doing a 40 var type approach? I might actually frame it in a different way and say, why is the 40 var cost function not suitable? So this plot just shows the JQ term over time for the second case study. The black is what you get from the 40 var approach, and the gray is what you would get if you were to just plug in the true values into the cost function. So you can see that you're getting a lower J with the 40 var method, which essentially means that we're minimizing an inappropriate objective function, which is somewhat unsurprising given that our errors are clearly not mean zero and of constant variance and not even really Gaussian. Okay, so we also examined the effects of these different uncertainty quantification schemes on assimilation and forecast outcomes. So we used a typical ensemble transform Kalman filter that's very popular with a fairly large ensemble size, so we don't have to worry about the effects of localization and small sample errors. And the main point I wanted to stress here is that you really get an improvement in forecasts even at longer lead times by properly accounting for model uncertainty. So here we just looked at 3 different forecast scores, so the CRPS and the log score, both of which measure reliability and resolution, and also the RMSE. So across a range of different forecast metrics, you really see an improvement. Finally, I just wanted to stress, again, the importance of accounting for non-Gaussian uncertainties. So this shows a particular snapshot during the assimilation process. So on the left, we have what the model simulation given the analysis from a previous time. The middle shows the sampled model error density, and the last plot shows the resulting forecast or prior. So the red is from the proposed approach, and you can see that by resolving these bimodes, you get a much better forecast, particularly in comparison to these to the analysis increment type approach, which requires a Gaussian with a much larger variance in order to prevent divergence or drift of the hidden variables. Okay, so to summarize, we proposed a method for quantifying model uncertainty due to unresolved subgrid scale processes. It's really just a step in this direction, and there's a lot of assumptions that need to be relaxed, and there's ways that we can also improve on it. The difficult conditions that there's no dynamical equations of the fine scale process and only partial observations of the coarse scale process. And also we really want to keep our prior assumptions as minimal as possible, but we can see that we can get an improved representation of model uncertainty, especially beyond just blindly assuming that everything's zero mean Gaussian. So we're currently working on extending this approach for including observation error through a maximum likelihood type of approach, but still trying to maintain the ability to detect these non-Gaussian complicated error structures, and also it's important to look at scalability. Thank you very much.
Thank you very much, Dr. Pathiraja. Okay, are there any comments or questions?